Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, chapter 2-7 is future value of investments, and the future value of a single deposit investment, periodic investment, biweekly, future value of a periodic deposit investment are all topics in this chapter section. Okay, so the first thing I have here is future value of a single deposit investment. That is the key right here, single deposit. If you're going to put money into an account, say you got married and you have gift money, you want to put it into an account for your kids' college fund, then you would take that lump sum money, invest it into some kind of savings account or something with interest, and you never add any more money to it. Put the money in, you pretend it's not even there. 20 years down the road, you withdraw it and see how much interest you've earned. All right, another way is periodic deposit, which means you're going to add periodically an amount of money to it. It could be every paycheck, it could be once a month, it could be once a year. Okay, and here's the formula. And the formula for the single deposit is just the compound interest formula. And as you can see, it's just in here, right here, it's the same thing. And then we're just going to subtract 1 and then divide by R divided by N. And that will give us our periodic deposit. Okay, so here we go. So B is the balance at the end of the investment period. P is the periodic deposit amount. R is the annual interest rate expressed as a decimal. N is number of times it's compounded in 1 year. And T is the length of investments in a year. So example 1 says Rich and Laura are both 45 years old. They open an account at Rhinebeck Bank with the hope that it will gain enough interest by their retirement at age 65. So right there, they're going to have this loan for 20 years. They deposit $5,000 each year. So it's annual. So it's going to be periodic, a period of 1 year, into the account that pays 0.0125 annually. What is the account balance from Rich and Laura retire? So we write B equals P parentheses 1 plus R over N to the power of NT minus 1, close the parentheses, divide by R over N. So over here, I'm going to write P equals 5,000. R is our rate, 0.0125. N is compounded annually, that's 1. And T is time, that's our 20 years from age 45 to 65. So this is going to be 5,000 times parentheses 1 plus our rate, 0.0125. over 1, which I didn't need to write because anything divided by 1 is itself, to the power of N, which is 1 times T, which is 20. Okay, all divided by R, 0.0125 over N, which is 1. And again, I didn't need to write that. So I'll simplify that when I put it in my calculator. So here we go, 5,000, parentheses, 1 plus 0.0125 divided by 1 is just 0.0125, so I'll just leave that. To the power of 1 times 20, which is simply 20, minus 1, close the parentheses, divide by 0.0125 and hit enter. And I got 112,814.89. $814.89. Okay, so that $5,000 they invest every year. So over 20 years, they will have invested 5 times 20 or $100,000. They will only have made $12,814 on the interest, adding $5,000 every year. So it'd be $112,814.89 will be their balance at the end of 20 years. Okay, so the check your understanding says how much more would Rich and Laura have in their account if they decide to hold off retirement for 1 more year? for an extra year. So they're going to retire at age 66. See if you can do this and come back, see how you did. So here we go. B is going to equal 5,000 times 1 plus 0.0125. The interest rate didn't change. The number of times compounded didn't change. But now the 20 became 21. That's all that changed. All over 0.0125. Now let me show you something in the calculator that'll make this easier. If you hit second entry, it'll bring back what you just typed in, and now I can arrow back, and all I have to do is change that 0 in 20 to 21 and then hit enter, and I get 119,225. and 8 cents. So how much more? We would take that 119 minus 112, 814.89 and subtract, and that would be 9. Let's see, that's a 4, that's 10, 9, 9, 9, 8, 1, 0, 1, 9, 8, 12, 4, 6. $6,400.19. Okay, so that's that one. Extend your understanding. Carefully examine the solution to example 1. During the computation of the numerator is the 1 being subtracted from the 20. Explain your reasoning. Okay, so the answer to that's definitely a no. Using the order of operations, 1 plus 0.0125 to the power of 20 will be computed first. 1 is subtracted from that value after, not from the exponent of 20. Okay, so that minus 1, what they're saying is this minus 1 right here gets subtracted after this computation is done, because the calculator does follow order of operations, and subtraction comes after exponential, exponents and multiplication. Okay, example 2 says how much money or how much interest will Rich and Laura earn over the 20-year period? So if I go back and I look, I think I've already said it. They made $112,814.89. So $112,814.89 is what they made, minus $5,000 times 20 years. Remember, they put 5,000 in every year. So that's going to be $112,814.89 minus 5,000 times 20, which is $100,000. So the difference is just going to be that $12,814.89. Okay. And that's how much interest they earned. So check your understanding. It says use example 1, check your understanding. How much more interest would Rich and Laura earn by retiring after 21 years? I think we've already done that. We have. Okay, so no, we haven't answered that yet. What we need to do is figure out this 21 here. And they made $119,225.08. $119,225.08. in 21 years. Okay. And so since it's another new 5 years, they would have invested another 5,000. So what I need to do is take that 119,000 we achieved on the last page, subtract the 5,000 that they would have had invested in that new year, and put 5,227. So it's now 117,225. Did I do that right? No. 9 minus 5 is 4. Hello. 114,225, and they made 12,000. So subtracting that other 100,000 that we didn't subtract yet, Okay, so it should be 105,000 I subtracted, but that would have given us $4,225.08. Or I'm sorry, 14,000. Subtract the 12,814.89 from the 20 years, and the difference here would be what we're looking at. So it's going to be 9,10141. So it's $1,410.19 more. So all I had to do in that one is what we did up here. Take the new balance that we got on the previous page and subtract 105,000 instead of just 100,000, and then take the difference of the two. Okay, example 3. Linda and Rob open an online savings account that has a 1% annual interest rate compounded monthly, and they're depositing $1,200 every month. How much will the account be after 10 years? So we're going to write the formula. B equals P parentheses 1 plus R over N. Close the parentheses. I should have a second parentheses there, right? Parentheses to the N times T minus 1. Close those parentheses and divide by R divided by N. Over here, I'll write P equals principal $1,200, $1,200 every month. R equals 0.01, N equals compounded monthly, that's 12 times a year, and T is time, number of years, 10. So there's what we're going to substitute into this equation, $1,200 times parentheses twice 1 plus 0.01 over 12. Close the parentheses to the power of 12 times 10 minus 1. Close the parentheses, all divided by 0.01 over 12. And that is going to give us our B. All right, so here we go. 1,200. Parentheses, parentheses, 1 plus 0.01 divided by 12. Close the parentheses. To the power of 12 times 10, I'll just put 120. Come out of that, minus 1. Close the parentheses. I'm going to hit enter here, and now I'm going to hit divide. So I've done the numerator already. And then in parentheses, just so it knows what I'm doing, I'm going to do 0.01 divided by 12. And make sure that it knows that that's my denominator, and hit enter. And I get 151,379.85. Okay. So in 10 years, if you're depositing $1,200 a month, that's $144,000. I'm sorry, $14,400 a year times 10 plus the interest. So it's $151,379.85. All right, so check your understanding. It says, would opening an account at a higher interest rate for fewer years have insured Linda and Rob at least the same final balance? And not necessarily. It depends on what the rate is. So it says not necessarily. It depends on the principal rate for starters and the length of time you're going to have it opened. So those are two other factors that can make it or break it. All right, so example 4 says to construct a graph of the future value function that represents Linda and Rob's account for each month. Use the graph to approximate the balance after 5 years. Okay, so this is a pretty simple graph. It's going to grow at a constant rate. So it's going to be linear. And if you don't invest any money, $0 then you're going to have $0. So the 0, 0 is going to be included, the origin. So we're going to have a line going through the origin. So we're going to let X represent each of the monthly interest periods. The minimum value of X is 0, which corresponds with the opening of the account. The maximum value of X is 120 because Linda and Rob make deposits for 120 months, which is 10 years times 12 months. Okay, so use a graphing calculator to graph the future value function. So we could go into the calculator, clear, go to y equals, clear, and what was that function? It was 1,200 parentheses 1 plus, and it was 1%, 0.01 divided by 12 compounded monthly. Okay, close the parentheses, to the power of 12 times 10, which is 120, minus 1, close the parentheses, divided by, and I'm just going to put the denominator in its own parentheses, 0.01 interest rate divided by n, which is 12 times a year. And hit enter and hit graph. Okay, so as you can see, you can't see anything here because we're only going from 0 to 10, 0 to 10. So if I hit zoom and look for fit, it's right here. Error window range. Okay. Interesting. So window. X minimum is going to be 0. X maximum is going to be 120. I didn't change that. Y minimum 0. And now let's hit graph and see what happens. Zoom. Fit. And it's not graphing properly. Window range, window. Okay. 0 to 120. Minimum, Y minimum is 0. And let's see, what would Y maximum be? 151,379.85. That's correct. For some reason, this calculator can't graph that. Okay, so let's do something different. Okay, I should have realized that when I graphed that it was a horizontal line, which means it's a constant function. I don't have any variables in here, so this is just a value, and it's going to be that 100 and some $1,000 that their account was worth, 151,379, and it's going to be a horizontal line there. In order to graph this for variable number of payments, that's being months, I don't want this to be 120. I want it to be a variable X. So now when I graph that, that's what it should be. So when X is 0, it's 0, 0. When X is 5, and so on and so on. So I apologize for that. There's the graph. And what it would look like zoomed up would be this here. Okay, so approximate what the graph value would be after 5 years. So after 60 months, which is 5 years, it would be approximately $74,000. So the way you would do that, just look here. 5 years is 60 months, go over, and it's 70, and they approximated it to be $74,000. Okay, so all I had to do, again, going back here, when I plugged it in, I needed my exponent to be X, which is the number of payments, monthly deposits, $1,200, 1, 2, 3, 4, all the way up to 120 times. Okay, so that's why it stops here at 120. It should stop right there. Okay, check your understanding. It says construct a graph for Rich and Laura's situation in example 1. Okay, so I went back and here is example 1. So all they wanted us to do was graph this. So just to save time, I will just show you. You're going to put that in your calculator. and it's going to come up with a graph that looks something like this. Okay, so there's the answer to that check for understanding.